look, we have already learned few things which will be applied over here. So, see, in this chapter, the most important things are right hand thumb rule, and this thumb rule is actually applicable for variety of things. Like if you have a current loop, current wire, so what will be the direction of the magnetic field? For that you can apply. Rather than rule, you can apply for loop, current loop to calculate the magnetic moment. Rather than rule, you can apply for the cross product. Okay, when you have two vectors A and B. So this is very important here. So far what we have learned? We have learned that a current wire creates magnetic field around it. So it will create magnetic field around it. If I keep a current carrying wire in a magnetic field, it will experience a force which we know can be written as, this is a force, can be written as I, length of the wire, the part which is inside the magnetic field. So L cross B is the magnetic field. So this is the force. Okay, and magnetic field for a long wire you can find out using Ampere's optical law, that is mu naught I by R. If R is the radius of this Amperian loop. So these are the things we have already learned. So today I want to see when a conductor placed in a magnetic field experiences a force. So this is called motor effect. This is called motor effect. Okay, someone is saying my voice is not clear. Just a minute, I will try with my ear plug because it has been giving me some trouble. If you will have to confirm me whether you are able to hear or not. Are you people able to hear me? Can you message me, Kishore? Can you message me and tell me whether you can hear or not? Actually, I am using my earplug now. Sometime back, I was just speaking to my computer speaker. You have to check whether you are able to hear my voice now. Okay, nice. So it is very clear, it seems. So I will go with this earplug. Okay. Thank you, Kishore. Yeah. So when I have a conductor carrying a current, when I have a current carrying conductor carrying some current, so what it does actually, it experiences a magnetic it experiences a force due to the magnetic field when it is kept in a uniform magnetic field. Okay, so that way, using that particular notion, and that particular notion is actually called motor effect, and using that motor effect will be that motor effect we can apply in our practical life. That's what I wanted to say. See wherever there is something to rotate, we use motor, right? I hope you people agree with me. We generally use motor, and that motor, yeah. So okay, so you can look here. This part we had already discussed in the last class, but still I'll just recap for your sake. Uh, See, if you can look here at this figure properly, I have a rectangular loop over here. A, B, C, D, and A. This one, rectangular loop. And look, there are two semicircular arc like that. These are called slip ring. You might have already learned in your previous class also. This is another slip ring which is attached to the uh, two ends of this current carrying rectangular loop A and D. So this part are connected to this slip ring, and you can see this kind of attachments. So this is called actually carbon brush. There are two carbon brushes, and those carbon brushes are directly connected to the battery. Okay, so when the slip ring is attached to the carbon brush, they will be connected to the, so this whole loop will be connected to the series, this circuit, and current will flow in the direction. Suppose in this situation current is flowing from A to B, B to C, C to D, and D to A. So in this scenario what is going to happen, uh, you see here, there is uniform magnetic field created by electromagnet, which has north pole here, south pole over here. And this rectangle has its length as B and breadth as A. Okay, and in this particular arrangement, the plane of the loop is in the direction of the magnetic field, or I can say the magnetic field is in the plane of the loop. So what happens when current start flowing through the loop? So this AB and this CD, these two arms of this rectangular loop will experience certain force. So that can be obtained from either using Fleming's left hand rule. Okay, either Fleming's left hand rule, or I'm sorry, I'm actually not able to do anything with this presentation. So either I have to restart the laptop, or I have to continue with the textbook itself. Okay, let me check if I can write in the Word or Paint. Maybe I'll try writing in Paint. If please, you people have to excuse me today, otherwise I'll take little time, actually 10 minutes almost. If I restart the system, it will take almost 10 minutes. So that I am not going to do. Okay, so I'll go with Paint so that I can write something and tell you. Okay, so I hope you people are able to see the screen, white space. Okay, so I'll choose red color, maybe this one. So you people are able to see this, right? Okay, so this is one problem here. So rubbing I have to do like this, maybe. Yes. Okay, so things are a little okay now. So what I'm going to say is this, that when you have a current carrying wire, okay, current carrying wire in a magnetic field. Suppose this is current. Uh, this is a current carrying wire in a magnetic field which is into the plane. Suppose. So how to calculate the force or the direction of the force for this case? You can use either right hand rule of cross product. So if you just do that, you will see the force will be in this way, in this particular case. Okay. So force, magnetic force on this particular case will be this way. Okay. You can use either Fleming's left hand rule. Okay. Or you can use right hand rule for the cross product. Okay. Right hand rule for cross product. So using that. So look here then in this book, in your book, if you apply this right hand rule for cross product, for this A arm, the force will be in the downward direction. Okay. If people can demonstrate this right hand thumb rule, because the current is going in the direction of A to B, so you can stretch your 4 fingers towards that and then bend them or curl them towards the magnetic field direction. So magnetic field is in this way, N to S. So that will be in the downward direction. Similarly, if you can apply right hand thumb rule for this CD loop, CD part of the loop, CD arm, you look the force, direction of the force, magnetic force on this part, this arm CD will be upward direction. Okay, in the upward direction. So if somebody doesn't know what is right hand thumb rule and all, if people will be having like if people can go through various YouTube videos and images are there in the internet. Actually, I had my things in the presentation, but I am not able to show you here due to some difficulty for today. Okay, if you people have any difficulty regarding how to like apply the right hand thumb rule, Fleming's left hand rule, or any conceptual things, if people can ask me, okay, either during the class or maybe after the class, you may, like, other people can let who does not have any doubt. But if somebody has any doubt, I can extend the class for 5-10 minutes. Okay, you people can ask me. Okay, otherwise there is no class or no extra time for doubt clearing and all. Okay, somebody is saying I can teach in Tamil. I know I cannot actually. I'm a Bengali guy. I don't know how to speak Tamil. If people can speak me in Tamil, maybe I can understand somewhat, but I cannot speak. Anyway, so I can see that the force, there are two forces, equal and opposite. See, the forces will be equal in magnitude but opposite in direction. You look here, this figure. So this figure exactly here. So AB arm is this one, and another arm is this one, CD. So and they are connected by BC, right? So I can say the force is, like, see, one is upward, downward here, another one is upward. So this is what is shown here. This is what is being shown here. Okay. So see, if there are two forces, equal and opposite forces, okay, there are two forces equal in magnitude but opposite in direction, and at the same time the line of action of the forces are not same. See, line of action of force is this way, this way, if I can draw this, so this way, and line of action of forces for F2 is this way. Okay, so since they are not acting in the same line, so they cannot cancel each other. So what they constitute is a torque. They will create a rotational motion on the object or a turning effect on the object. So that's why these two forces are called couple, and this couple will create a torque in this loop. And see, according to this figure and the direction of the forces and all, it will actually rotate in the clockwise direction. I'm sorry, anti-clockwise direction. If you can see anti-clockwise direction, so B will go to C. See here, it is shown here. See this arrow, okay, and it will rotate. If you can fix 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 a pivot over here, so it will rotate about this. See this straight line about that axis, it can rotate, okay, can rotate. So the torque is actually creating the rotational motion in this loop. All right. So this thing again we'll see while learning, I think in the induction part, how to create AC, how to generate AC current. Okay, there also we'll see this kind of rotation. Okay, and that was necessary for producing AC current. So in this case, we'll quantitatively, if we want to calculate the uh, forces on the arms, so what will be those? I'll show you here. So look here. So the current is I. See the length of this AB wire is B. Okay, and I have to take the direction in the direction of current, so it is going A to B. So you and B is actually magnetic field. Magnetic field is perpendicular to this lane. So cross product says that B cross L will be actually this. Since both are 90 degree, I can write this as, oh I'm sorry, this is B, magnetic field. Magnetic field created by this electromagnet. So I can write this as IBB. So this is the force, magnitude of the force. Magnitude of the force will be same for both. So both F1 and F2, what I was showing you here, like your F2 is this way, upward, F1 is this way, downward, F1. And see, look, this is BC. This is actually BC. And what is the axis of rotation? I have to calculate the torque about the axis of rotation. So this is the axis of rotation. Okay, generally torque is written as tau. Okay, and this is actually if I write in terms of scalar, it is the multiplication, or you can get the torque by multiplying one of the force. Suppose since they have both same magnitude, I'll take F into the perpendicular distance between the line of action of the force. So in this case, this is A by 2, this is A by 2, the whole will be A. So I can write F into A. So F I have got again, F is this one, okay, IBA. So if I write that, so I can get I into A into B into B. Now look, this A and B, this this is the dimension. See, this is your B length and A is the breadth. So I can write that as area of the loop. Now another, so this is actually the torque you experience here. And look here, so this IA, this term we will be defining as a new term. Okay, so torque we have got uh, IA and B. B is the magnetic field. I into A, what is I? I is the current through the loop, and like in the loop, and this A is actually the area of the loop. So this current into area, this can be written as like denoted by a small m, and in fact it has a new name. This is called magnetic dipole moment. Okay, this is called magnetic dipole moment. Okay, dipole moment. So this is called magnetic dipole moment. So what we have got here is that I'll just clean everything. and write again. So what I have got now is, so I'll just go to your book then. M B. Okay, this is the scalar path M into B. So I'll just show you from the next part of your this theory. This factorially you can write this as M cross B, but how to show you that is here. Look the next part of it. So earlier my loop and the magnetic field direction of the loop and the magnetic field was in the same direction, but in this case your loop has been taken kept tilted, okay, in a tilted manner, so that the magnetic field is in the same direction as in n to s, north to south, but the the normal to the loop area or area vector of the loop is in this direction at an angle theta. So as I told you that there is a new term now, magnetic moment, and that magnetic moment is a vector actually, and that vector can be, that vector has a direction in the direction of area vector of any loop, area vector of any loop, okay, that is along the direction of outward normal to any loop area, okay. So that's why now in this case, if I keep my loop tilted with magnetic field, then what we'll do, what we'll get actually, see, we'll get this figure. I'll get both f1 and f2 as it is magnitude wise, but now since this is BC tilted, look, this is BC, so the torque, the definition of the torque was actually the force, magnitude of any one of the force into the perpendicular distance between the line of action of the forces. So here in this case the perpendicular distance, I'll just take this figure. Okay, so you can see this figure. So in this case, you know, the perpendicular distance is this. Okay, I'll just draw maybe here. Look, this is the magnetic field direction. Okay, and your loop is like this. So BC, this is BC. This is a BC line. So with that, actually this is actually perpendicular to BC. So which is the direction of AM also, and AM vector means magnetic moment vector as well as area vector, because area vector will be perpendicular to the area also as well as the any side of the loop also. Okay, so this is the BC side of the loop. So BC, you have the total length actually A. So if this is the midpoint, I say, so this is your A by 2, okay, and this is also A by 2, and this is the angle theta. Now what you have to find out actually, you have to find out, see, there are two forces, one is along this direction and another one is along this direction. Now this one is the other one. So you look here, this is the perpendicular distance. Now this one, if I say this is D, this is the perpendicular distance between the forces. So how to find out that? So to find out that perpendicular distance, okay, so you have to see this figure, okay. So this is B. So if this is theta, see, this will be 90 minus theta, isn't it? Actually my drawing is little uh okay, just a minute. this part will be going like this. So this is the perpendicular distance. Okay, now see, this will be, this angle will be 90 minus theta then, because this is whole is 90° with AM and this line. Okay, so I have to find out this length, this particular length, this length. I have got F1 and F2 magnitude are equal. I'll write the same force as the F is here, IBB, the same force, but the perpendicular distance is now different. So this is actually, look here, this will be 90 minus theta, and you know, like this is, again from here you can see this is also 90°, this is 90°. Okay, this is 90°. So this will be actually your theta. When you, so in this figure in your book, what is given, the figure you see in your book, so this particular angle will be theta. This particular angle will be theta. So what I'm showing here. So this is F1, this is F2. So this angle, if you see, this is a, so this is total 2a. So if this is theta, this is a 90° angle. So you can see this part you will get as like, so this you will get as a sine theta. Okay, a sine theta. You people can see to it this geometry and see how whether you are getting the perpendicular distance between this f1 and f2 as uh, a sine theta, a sine theta. You will get that, and if you multiply with this, okay, this force, so then you will get the torque. So look, I'll write IBB into this perpendicular distance. Okay, I'll just clean it and write again. So you can see torque will be the force IBB and the perpendicular distance a sine of theta. So this one. So A and B will give you again area. So I into A. So A and B, length and breadth. Okay. IA, and this is B and sine theta. Look, this IA we had defined as M, magnetic dipole moment, and this is B, and then sine theta. So can we write this torque in terms of vector, this as M cross B? I hope you agree with me. So this is a cross product when I get sine theta. Okay, so M cross B. So that is what is there in your book. You can just look that. So you get, finally we get here. Okay, so which here they have told you that this M is magnetic dipole moment, and we can use the right hand thumb rule to find out the direction of the dipole moment. Okay, so if you have a look, see, I'll tell you how to apply right hand thumb rule for finding out the direction of the dipole moment. If you have a current loop like this, okay, current loop like this, and you know current is flowing like this, then your magnetic dipole moment, if suppose this is going through the center and this is in the plane of the paper, okay, okay, this is the center which is passing through the loop. Okay, look here. So right hand thumb rule, you have to put your all four fingers in this way. Okay, along the direction of your fingertips should be along the direction of the current, and try to hold this loop with this is kind of grip rule, and your thumb, when your thumb is pointing this way, so you can just apply this now itself, and you will see your thumb will be in this direction. Okay, in this direction. So magnetic moment will be in this direction for this loop. If the current is in the opposite direction, okay, suppose the current is in the opposite direction, in this case itself I can show you, your thumb will be in the opposite direction. Okay, so in the opposite direction, if the current is along this direction, so the position of the finger will be different, and you look, the direction of this magnetic moment will be in the opposite direction. Okay, in the opposite direction there. Current direction is if this way, then magnetic moment will be in this direction. You can apply your thumb rule or grip rule properly to find out that. Okay, so all right, so this will give you the idea of the direction of the magnetic moment M. Okay, so let us go to the textbook. Okay, so actually if you look here, this is tau, this is the torque M cross B. The similar expression we have seen in the first chapter, when you keep an electric dipole in a uniform electric field, so you also get to see that that electric dipole will experience a torque which can be expressed as Pe cross capital E. Pe in the sense a dipole moment for electric, like electric dipole moment, and this is the electric field, uniform electric field. So whatever we have learned, these are all happening in the uniform electric or magnetic field. So these are the similarities. So there are similarities in this electric and magnetic cases. We'll show in the next section how similar are they. And see, since I have got magnetic moment as I into A, if I can make the number of turns in the loop more, so current will be more, then I can get more magnetic moment. If I get more magnetic moment, I can get more turning effect. More turning effect. Okay. And if I increase the area of the loop also, I can get more magnetic moment, and the tendency of the rotation will be more. So here I'll be discussing on interesting thing, that we have got the expression for the torque as torque. So what is happening when I keep a loop, rectangular loop like this in a uniform magnetic field, rectangular current carrying loop obviously. So in a magnetic field, uniform magnetic field in this way, suppose, so it will experience a torque, and this torque is due to actually the magnetic field and also the current. They are both current in the loop, so both are actually responsible for creating the torque. Okay, torque M cross B, and in the expression you can see, if I take the magnitude of this, I get MB sine theta. MB sine theta. So this torque, you look, this depends on the theta. If the theta is 0, the theta is 0, then torque is 0. Or theta is pi, then also it will be 0. Torque will be 0 when theta is either 0 or pi. That means, you know, if my wire, okay, if my so this actually this current carrying loop can be considered as magnetic dipole, as we have seen magnetic dipole moment. So M cross B similar to my P cross E. So P is the P. So if we compare these two, I can think of a loop, current carrying loop, as a dipole, but this is magnetic dipole. I can think of magnetic dipole. A current carrying loop can be thought as a magnetic dipole.
Okay, so that magnetic dipole, when the direction between say M and B, that means dipole moment, and B is 0 or pi, that means when the dipole, suppose the magnetic field is in this direction, or and magnetic moment also in this direction, so they have angle between them is 0. Okay, theta is 0. So this is one case, uh, which is actually gives you the torque 0. So this is one condition when torque is 0. So if your magnetic moment, sorry, magnetic field is this way and magnetic moment is in this way, so what you get is actually pi is also 0. So that time also you'll get uh, that also will give you torque 0 over here. But where the torque is maximum, when your theta is 90 degree, when your theta is 90 degree, so that time you will get torque maximum. So if you keep your, see here in this case the torque will be maximum because the current carrying, so like if this magnetic field and the m vectors are perpendicular to each other, then there will be maximum torque. Okay, that means maximum rotational effect. Okay, that's why we'll be seeing in moving coil galvanometer it is always desirable to keep the loop in a magnetic field, uniform magnetic field, and also the direction of the uniform magnetic field has to be perpendicular to the direction of the magnetic field. Okay, the direction of the magnetic field will be perpendicular to the, this is suppose B, this should be A or M. M is the magnetic moment vector, A is the area vector. So this has to be maintained. We'll see that in our next class while discussing moving coil galvanometer. So yeah, so this is all about here. Now what we'll do, we'll just go to the next section. Circular current carrying loop as a magnetic dipole. As I told you, uh, here it is, here we'll be defining circular current loop as a magnetic dipole, but it is generalized for any current carrying loop, not only circular loop. But in this case, we will show only for uh, circular loop. Let us see what we can get from the circular loop, how we can establish that magnetic field, the elementary unit of magnetic field or elementary source of magnetic field is current carrying loop. So if you remember, we had calculated magnetic field for current carrying circular loop on its axis. I hope you people may remember this. Okay, so at certain distance x we had calculated, suppose the area, radius of this is r. Okay, radius of the loop is r, and we had calculated magnetic field on the axis of this loop, on the axis of this loop. What was the expression? You can see the expression was like this: b is equal to, I'll just write in terms of scalar itself, so mu 0 I r square divided by 2 into x square plus r square whole to the power 3 by 2. Okay, I hope you agree with me. Now look, if I consider this distance, this distance x from the center of the loop is much greater than, much greater than r. R is the diameter, radius of the loop. If that is greater than, much greater than the point where I'm calculating the magnetic field, that distance from the center of the loop, then see I can just simply neglect this r square term nearly equal to 0, I'll say. Okay, and then this expression, see this expression actually eventually become this mu naught I r square, okay, divided by 2 pi into x cube. Okay, Now I'll just multiply pi both in the numerator and denominator. Pi r square divided by 2 pi x cube. See this pi r square, this is nothing but the area of the circular loop. So I can write that as mu naught I into a divided by 2 pi x cube. So just few minutes back we have learned what is this called is magnetic dipole moment. So I can write this as mu naught n by 2 pi x cube, or if I multiply even one more 2 up and down, so I get mu naught 2m by 4 pi, mu naught by 4 pi to 2m by x cube. Look, this expression you might have learned in case of electric dipole also, when on any axial point for an electric dipole, electric field created by any axial point, we have got what we have got is actually 2p by 4 pi epsilon naught, 4 pi epsilon naught into x cube at any distance. I hope you remember this. Okay, so these two, you can see these two are actually very similar. This is for electric dipole. Okay, and this we have got now for a circular loop. That means, can you tell me from this analogy, okay, from this analogy, can I tell that the circular current carrying loop is acting or behaving as a magnetic dipole, similar to your electric dipole in case of electric, uh, in case of electric dipole. Okay, if you compare these two, you definitely can tell me that a circular loop, obviously current loop, circular current loop is acting as a magnetic dipole. So this is what we can find out. Even not only on an axial point, from the same analogy, we can find out the magnetic field for a magnetic dipole. For a magnetic dipole, if I say, actually magnetic dipole, you will learn actually magnetic dipole is denoted by an arrow head. So a line with arrowhead. This magnitude will be given by the length of the arrow, and direction will be given by this arrow. Okay, so if I have any dipole kind of that, magnetic dipole kind of that, so it will create a magnetic field on axis any point here. This is 2 mu naught by 4 pi 2m by x cube, and any point on the perpendicular bisector, you can write from the analogy. See, for electric dipole, we have got p by I think 2 pi x cube kind of that. Okay, so in this case also we'll get b as m by 2 pi x cube. Okay, you can look from your book that from the analogy we can write that a current carrying circular loop is acting as a magnetic uh, magnetic dipole moment. Okay, magnetic dipole. So you can look here, this part is very important. I'll just underline here. You look this part, this portion, you have to understand. So results obtained above can be shown to apply any planar loop, not only circular loop, any planar current carrying loop is equivalent to a magnetic dipole of dipole moment M is equal to I into A, which is the analogous or analog of electric dipole moment P. And note, however, a fundamental difference is, what is the fundamental difference? This is important. The electric dipole is constituted by two elementary charges which are called monopole, plus Q minus Q. But in case of magnetism, there is no kind of monopole exists. There is no magnetic charge, positive magnetic charge or negative magnetic charge. You should not like confuse with north pole and south pole as positive charge and negative charge. Okay, there does not exist any monopoles, and only elementary unit for the magnetic field is a current carrying loop. Okay, current carrying loop or magnetic dipole, we should say magnetic dipole. So that is the only elementary source of magnetic field. Like your electric field, elementary source can be a point charge, can be dipole, etc. Okay, but in case of magnetism, the source of your magnetic field will be only current carrying loop or circulating current. So that's why Ampere actually suggested that magnetism is due to circulating current, but there was few things not correct. Like this seems to be partly true. No magnetic monopoles have been seen so far. However, elementary particles such as an electron or a proton, they don't have such kind of circulating current, but you can use that model as well in case of electrons also. But they have intrinsic dipole, magnetic dipole moment, even though we cannot assign any circulating current to those kind of cases. Okay, now we'll see another point. Magnetic dipole moment of a revolving electron. This is also very interesting, and there can be numerical problems from this particular portion. So there are actually in many exam, either your competitive exam or maybe in your school like board exam also, there are questions from this particular part. Okay, so then we'll just try to learn this part quickly and then we'll finish today's class. I'll not take too much time. Maybe since I have started 5 minutes late, I'll just take 5 minutes extra uh, in this case. Okay, so look, I have here, you look this figure. If I just take it, so I hope you people are little bit aware of, at least you people are a little bit aware of the Bohr model of atom, even though you have your like in the next, in this, I think 12th chapter or 11th chapter we'll be learning that. 12th chapter maybe in this NCERT textbook, second part 12th chapter we'll be learning that. Okay, so Bohr model, Rutherford models, etc. we'll be learning. I'll just quickly tell you what little bit about this model. About like according to Bohr, Niels Bohr, he had given first the almost like classical. This is also classical idea. It says semi-classical idea of the structure of atom. Okay, structure of atom. So what he has said, that the most of the mass of the atom is situated in its nucleus, and nucleus is positively charged, and the positive charge will be exactly equivalent to the electronic charge you have, like number of electrons you have in the atom, so that this positive and negative charge they can uh, make them neutral, make the atom neutral. So according to Bohr's model, uh, the positive charge is situated in the nucleus, and the negative charges, which are the electrons, they are just revolving in particular orbits, few orbits, where actually Bohr had given that quantum knowledge of, or quantum idea of Bohr orbit, that is the orbit for which the angular momentum will be n h by 2 pi. So those orbits will be, this is the number of orbit or quantum number it says. This is the number of orbits. So these are the orbits allowed for this. So uh, for now you remember that positive charges situated at the nucleus, and electrons are revolving just like your planetary motion. Electrons are revolving in various orbits, but those orbits are not arbitrary. They follow this rule: L is equal to nh by 2 pi. Okay, they're revolving just like Earth and other planets are revolving around the sun. So the electrons also will be revolving around the nucleus. And see, in case of gravitation, you have seen the gravitational force was supplying the centripetal force for the circular motion, and in this case electrostatic force Je plus, and this is minus E by 4 pi epsilon naught. If this is small r, this is the small r square. This will give you mv square by r, that is called centripetal force. And by the action of this force, the electron will execute the circular motion. Okay, execute the circular motion. And when an electron is executing a circular motion, you look, if the electron is moving in this direction, you look the direction in this direction, then the current will be flowing in the opposite direction. You have learned in your second or third chapter, I think second chapter, second maybe third chapter, you have learned that the current is flowing in the opposite direction of the motion of the electron. If the electron motion is this way, current direction is in this way. So current will be in this direction, okay, opposite to the direction of the motion of electron. However, since the charge is moving in a, like it is moving in a motion, so it will be creating a orbital current. That's what we can say, orbital current. So how do you calculate the orbital current? This is, like, we know the total charge by per second, that is called current. So in this case, E is the charge and T is the time period, okay, which I can write as, see, time period I can write as 2 pi r by V. Okay, I'll just put it there. So what is the current I am getting now then? Current I'm getting is, if I put this E by 2 pi r by V, so EV by 2 pi r, okay, 2 pi r. So this is the current. Okay, now if I want to calculate magnetic moment, which I can write as mu L over here, mu L in the sense this magnetic moment due to the orbital motion of the electron. That's why this is L is given orbital motion. And see, I can write I into A. A is the area. So A I can write as, so E I have got EV by 2 pi r. So here I can write pi r square. Pi goes off, 1 r goes off with one of this. So what I get is E by 2 and then r into V. I'll just clean everything and write again this equation, then it will be clear to you. So the magnetic moment, which I have written here as mu L, magnitude I am getting is E by 2 into V into R. So this is the magnetic moment. Okay, if I just multiply M both up and down, look, I'll get E by 2M MVR. So this MVR I can write as angular magnetic angular mo linear momentum, that is angular momentum. Okay, this mvr is angular momentum. I can write as L. Okay, and if I get this ratio mu L, magnetic moment divided by angular momentum, so I get E by m, E by 2m. So this E by 2m, this ratio is called gyromagnetic ratio. What is this called? This is called gyromagnetic ratio. Some people pronounce it gyromagnetic. So as you are comfortable, or maybe your teacher, school teacher is saying, you can follow that also. So it is actually gyromagnetic ratio. Magnetic ratio. So if you know exam, they ask you to find out what is gyromagnetic ratio, you have to do this one. Okay. Now again, according to both quantum idea of orbit, we can write little more about this. Look what I can write. So I can write mu L is equal to, this is E by 2m. E is the electronic charge, and this is the L. L is actually L. I can write as in n is suppose a 1. Okay, so I can write as h by 2 pi again. Okay, this is h by 2 pi. So I can write E h by 4 pi. So L I have written, L I have written as h by 2 pi. Okay, from Bohr's theory, which we'll be learning in the 12th chapter, that time that this will be again clear. So E h by 4m, this is called intrinsic fundamental unit of magnetic moment, which is called Bohr magneton, which is called Bohr magneton. I'll just write once again, Bohr magneton. Okay, that is called Bohr magneton. So mu L, what we get is E h by 4 pi m, 4 pi m. So this has a value. If you just put everything, E as electronic charge, H is 6.6 to 10 to the power minus 34 joule second, and m is the mass of the electron. If you put all those things, so what you get in, like this will be 9.27 into 10 to the power minus 24 ampere meter square. So this is called Bohr magneton. BOHR, Bohr magneton. Okay, what is this Bohr magneton? This is the fundamental unit. Bohr magneton, Bohr magneton. Okay, so this is the fundamental unit of magnetic moment, fundamental unit of magnetic moment, which is given in your book. So I'll just show you the rest of the thing from your book. Okay, and then finish maybe in 2 minutes again. Okay, so you get, so look here, I have all the way. Okay, so here I have missed minus sign. See, this minus sign actually has certain significance. This minus sign says that the magnetic dipole moment, okay, the direction of the magnetic dipole moment and angular momentum, they have opposite direction for electron. If this is a positive charge, then this sign will be positive. Since it is electron, the angular momentum and magnetic dipole moment, they are oppositely directed. Okay, that's why this minus sign is there. Okay, if they are positive, then you can write as a positive. So I was talking about this part, and see that is called orbit. See, this is the actually fundamental unit of the magnetic moment, and this is called Bohr magneton. You will see here somewhere it is written. This is called Bohr magneton. Okay, Bohr magneton. So I'll stop it here. You people can read up to this portion. Next class, I think on Sunday, we'll be learning this moving coil galvanometer. And this moving coil galvanometer is very interesting. And that day we'll try to solve few numerical example as well. So, so for today, that's all for today. Okay. Uh, all right. So then I'll stop it here. See you all on Sunday. Okay, at the same like same time. Okay then, bye.